In this discussion, let us see two very important interview questions. Gradually you will get, just stay tuned. Now point here is, previously in our previous session we discussed about transformer at no load condition. Now we have to discuss about transformer, ideal transformer at loaded condition. Okay, so this is ideal transformer at loaded condition, okay. Now see here, if I want to close my switch, for example this is going to be transformer, okay, and here at no load condition, this is the scenario. Already you know, this is going to be V1, infinite source, infinite sinusoidal source, and here at no load conditions I0 current will flow. This I0 will develop pi naught operating flux. Okay, I0 and N1 will decide the operating flux pi naught, and pi naught and N2 will decide the induced voltage E2. At no load condition, the switch is still open, and pi naught and N1 will decide E1. Okay, now we can say that what is V1? It's an infinite source. Okay, so this is V1 is infinite source. Whatever you do, you will not be able to change the instantaneous waveform of this. In the sense, the amplitude and frequency cannot be changed, and sinusoidal nature of the source cannot be changed. Okay, now what is connected between V1 and E1? Nothing is connected. Actually, some people feel that no wire will have resistance. No, that resistance is going to be practicality. In the phase 2 we are going to consider. Okay, now see here, if V1 means if V1 is 100 volts, automatically E1 should be 100 volts only. Now V1 equal to minus E1 can be written, or V1 equal to plus E1 can be written. That's a different thing, but I can say that magnitude of V1 should be equal to magnitude of E1. Okay, magnitude of V1 should be equal to magnitude of V1. Now what is magnitude of V1? N1 d pi naught by dt at t less than 0. Because I would like to close the switch at t equal to 0. Okay, actually one very important thing we have to share here. At t equal to 0 I am about to close the switch. Okay, at t equal to 0 I am about to close the switch. Now some people think that because I told you two very important interview questions. For example, at t equal to 0 I am about to close the switch. At t less than 0, how much is the current flowing through this? 0. Now is this inductor or not? Yes, it's an inductor. Okay, so at t less than 0, current flowing through inductor is 0. If I close my switch at t equal to 0, immediately after closing the switch, how much current will flow through an inductor? Current should not be changed in an inductor instantaneously. So the moment I close the switch, immediately current flowing through inductor will be 0. So means, do we need to analyze transient analysis here or not? No, we are supposed to analyze steady state analysis. Okay, so basically I will tell you, for example, at your home ceiling fan will be there. Okay, so what will you do? You are going to switch on the ceiling fan, it will keep on rotate. Okay, so you are not going to play with the ceiling fan or your at home your fan saying like stop, will you play? No. Once you switch on the fan, it will continuously rotate in steady state. Okay, at starting, the moment you switch on, your ceiling fan will start accelerating. During that time, definitely transient will be there. But once it comes to steady state speed, it will continue to rotate at steady state speed only for most of the time. Okay, machines, basically I'll tell you, machines normally work in the steady state conditions only most of the time. So we do analyze machine in steady state conditions only. Normally machine will not be analyzed in transient condition. Okay, or we can add this. Okay, for example, if I ask you, why do we laminate the core? Of course, we are yet to discuss about eddy current loss. I know. Okay, but I know already that you know a bit of eddy current loss. Okay, or some kind of lamination. Okay, so if I ask you, why do we laminate core? If you say to reduce eddy current losses, may not be right, may be wrong. Okay, because basically laminations we do to reduce eddy current losses in machines. Okay, because in machines steady state behavior is important. Okay, kind of, for example, let me give you a small what do you say example. Okay, maybe on the highways, national highways, maybe 20 tire lorry. Okay, so 20 tire lorry will be there. Okay, so what are the design constraints of a big lorry? Okay, big vehicle, big lorry. Okay, so what should be the design constraints? Basically, that lorry or big vehicle will travel only in the national highways. Okay, so the moment they are traveling in the national highways, their steady state speed is going to be fixed normally. Okay, so normally in national highways, that such a big vehicle, they don't accelerate stop, just like, for example, if the steady state speed is 40 kmph, 40 kilometers per hour, it will continue to operate normally at 40 kmph only, steadily. But the diesel engine capacity is so big. For example, means guys might have like a bike, okay, two-wheeler. Okay, so for the two-wheeler bike, what are the important design constraints? Important design constraints are not steady state speed, okay, but important design constraints are transient behavior. Why? For your bike, you will accelerate, you will stop, because your bike two-wheeler is supposed to roam not at the national highways but inside the cities. Okay, so same diesel engine will be same. Capacity of your maybe bike is less, capacity of that 20 tire lorry is big. Okay, but the design constraints, if you see, for your bike they will specify, for example Apache and all, they will specify clearly 0 to 80 kmph with this many seconds and all. But no data sheet will give you for such a big lorry how much time it takes from 0 to 100 kmph or 0 to 50 kmph. They don't give you, because means my big vehicle in national highways is not supposed to accelerate, decelerate, no. But for your vehicle, for your bike, means acceleration will be there, deceleration will be there, acceleration will be there, deceleration will be there. Means that our machine is like a very big vehicle which roam in national highways. Means that steady state behavior, basically our machine will work most of the times in steady state conditions only. So steady state behavior is important. Now if you think of our Pulsar bike or maybe Apache bike, your two-wheeler, for your two-wheeler, acceleration, deceleration matters, not the steady state speed. Getting my point, right? Similarly, for example, your control system will be there. Okay, if you think of your control system, forward path will be there, feedback path will be there. Okay, so what is the purpose of forward path and what is the purpose of feedback path? Let us see. The purpose of forward path is it will transform bulk of power my machine. Okay, and what is the purpose of feedback path? It is supposed to transmit information such that if any error is there, controller will come and controller will make everything set right. Okay, so feedback path will work on transmitting information, forward path will work on handling huge of power, bulk of power. Okay, normally machines will work under steady state conditions only most of the time, which will handle bulk of power, which will be there in the forward path of the control system. Okay, now if you think of feedback path, basically one thing I'll tell you, measuring instruments, measuring ammeter, voltmeter, wattmeter, energy meter, whatever it may be, measuring instruments operating principles, at least analog measuring instruments operating principles, and our machines operating principles are same. In machines, how torque is getting developed in a motor, in the same way torque will be developed in your measuring instruments, that is deflection torque. Okay, so measuring instruments and machines work on the same operating principles, but design constraints are different because these are measuring instruments. Feedback path is measured because means just by seeing ammeter you will come to know whether if the current is set to be, for example, if the current is set to be 5 amperes, by measuring instruments you will come to know whether that particular current is beyond 5 amperes or less than 5 amperes, means that it is giving information. Okay, so machine is such a big thing, which is a power handling capacity of more, which handles bulk of power under steady state conditions most of the time. So for machine, steady state behavior is important. What are steady state behavior? Efficiency. losses, voltage regulation, speed regulation, voltage regulation for a generator, speed regulation for a motor, gradually you will come to know. Okay, so for a machine, steady state behavior is very important. And for servos, we say, which are there in the feedback path of control system. Okay, for servos which are there in the feedback path of control system, basically servos transmit information in transient conditions most of the time. Okay, so point is very simple. In transient conditions, for your bike, small IC engine, for a big lorry, very huge power IC engine. But for a huge power IC engine, steady state behavior is more important. For a small power IC engine like your bike, means transient behavior is more important. Okay, so for a servos are measuring instruments, how fast it is coming to steady state. For example, if you connect an ammeter, how fast it is coming to show you 5 amperes matters. Okay, so for servos, transient behavior matters. For servos, torque by weight ratio matters. For servos, raise time matters. Okay, so point to be noted here is very simple. What is that? What is settling time also matters. So for servos, whatever you do in servo, measuring instrument, okay, or DC tacho generator, okay, this is very famous interview question. Gradually you will come down, just stay tuned. Okay, for machines, whatever you do, it should be to improvise steady state behavior. In servos, whatever you do, it should be to improvise transient behavior. Operating principles of machines and measuring instruments are same. But the purpose is different, the application is different. Okay, now for example, if I think of machine, if you do laminate the machine, it should be to reduce eddy current losses, efficiency matters for this. But if you do lamination for this, for servos, kind of a DC tacho generator will have laminated core. Now can I say that DC tacho generator will be laminated to reduce eddy current losses? No, because what is the power handling capacity of servo? Information. What is the power handling capacity of ammeter? What is the power handling capacity of voltmeter? No, power handling capacity is nothing. But what is important? Information matters. Okay, so the moment if you think of servo, tacho generator, if you say tacho generator core is laminated to reduce eddy current losses is wrong. Why? To reduce eddy current losses means that you should have power handling capacity. Okay, now why do we laminate DC tacho generator? It should be, of course, in future I will show you, I will prove you that how this particular laminating the core will reduce time constant, I will tell you. Okay, but anyway here for servos, whatever you do in the feedback path of the control system, it should be to reduce time constant, to increase torque by weight ratio. Okay, so of course I'll give one more example now. Basically one conclusion now. What is that conclusion? Machines are supposed to be working under steady state conditions most of the time, which will handle bulk of power. For that, steady state behavior matters, kind of losses matters, efficiency matters. Okay, for the feedback path of the control system, kind of servos or measuring instruments means they will not handle power, so power loss doesn't matter, but they will handle information, so time constant matter, transient behavior matter. So whatever the instruments which are connected in the feedback path, they will transmit information mostly in the transient conditions, so transient behavior like time constant. Okay, transient behavior like torque by weight ratio, these are important things. So whatever you do in servos, it should be to reduce or to improvise transient behavior. Now, my measuring instruments should be analyzed for transient conditions because they will transmit information in transient conditions, but my machines should be analyzed for steady state conditions because in machines also definitely transient condition will be there. For example, let me come back to here. Okay, so if I close the switch, the load, initially transient condition will be there, but once it is closed, once transient die out, then steady state conditions will prevail. Now my machine is supposed to be working most of the time in steady state conditions only, so transient behavior is not analyzed. So I should not say the switch is closed at t equal to 0. So at t less than 0 the switch is open. So immediately after t 0 plus, current flowing through this will be 0. So transient condition has to be analyzed is wrong. Because once transient condition die out, most of the time it will work in steady state conditions only. Okay. Anyway, let me give you one more interview question. That is, servos will be there. Okay. So for example, servos will be there in the sense feedback path of the control system. Servos will be there. Machines will be there. Machines will be there. Okay. Normally, if I ask you what is the costliest part of the machine, okay, what is the costliest part of the machine? Can I say copper is costliest? No. Iron is costliest? No. No. Insulation is costliest? No. Bearings is costliest? No. But what is costliest part of the machine? It's a shaft. It's a shaft. Okay. So if you think of it, the center shaft will be there, no? Shaft will be there. Upon shaft, my rotor will be there. Upon shaft, my rotor will be there. Okay. Upon that, my stator will be there. Now, this particular shaft is there, no? Shaft is the most costliest part. Most costliest part. Okay. Means this discussion will stretch, but don't miss. Okay. Watch till end. Watch till end. Now, shaft is the costliest part. Why? Why? For example, generator or motor. Generator or motor. For example, this is the shaft. This is the shaft. And here motor is there. Here motor is there. Motor is there. To the shaft, load is connected. Load is connected. For example, for the shaft, this is the shaft. No, this is the motor. Motor will try to rotate the rotor in this direction. Okay. So this is particular motor. This is motor. This is shaft, which is connecting motor with the load. Okay, so motor is trying to rotate the shaft in this direction. Means that my motor is trying to rotate the shaft in this direction. But if you think of the load, okay, for the motor, what is the load? Means, for example, if I have brake drum, okay, so brake drum will be connected to the shaft, and to the brake drum we are going to connect springs like this, no, in our labs. Okay, so springs like this. Okay, so point here is simple. Means we are going to keep on tighten. We are going to keep on tighten such that in order to load the motor. Isn't it? So again, let me come back here. This is the shaft. This is the motor. My motor is trying to rotate in this direction. Okay, my motor is trying to rotate the rotor in this direction. But my shaft, my shaft is connected to the brake drum. That brake drum is trying to stop the rotor. For example, this is the brake drum. This is the brake drum. Okay, this is the brake drum and this is the motor. My motor is trying to rotate the rotor in this direction, but my brake drum is trying to stop the rotor. Is nothing but the load. Now, if you sit in between the shaft, means something is trying to rotate in this direction, something is trying to stop in this direction, means that mechanical stress will be there on the shaft or not. Okay, so if this is my motor, if my motor is trying to rotate the rotor in this direction, my load will try to stop the rotor in this direction, such that how much will be mechanical stress upon the shaft is going to be more. In order to bear the mechanical stress, okay, means if you directly take the iron, okay, liquid iron, if you pour, it will not be sufficient. Okay, means if you keep a mold of shaft of a round one and in a cylinder, if you pour, it will not be sufficient, because material will become brittle. So, means there are many methods in our, mechanical engineering, cold forging, hot forging. Okay, some methods are there. In the sense, cold forging in the sense, directly they will take the metal. Okay, so they will take iron, they will keep on hammer it, and then they will process through the lathe machine, such that this mechanical stress it will be able to bear. Okay, so just stay tuned, you will get the conclusion, because in machine, patience matters. Okay, with patience, you will understand machine. Okay, now if you think of the shaft, normally the moment it is machine, one thing will try to rotate in this direction, another thing will try to rotate in opposite direction or try to stop. Mechanical stress will be more. In order to bear that mechanical stress, we have some methodologies called as cold forging, hot forging and all. Because of them, my shaft is going to be the costliest part. Okay, so of course I am coming back. Okay, now if you think of shaft is the costliest part in machine. So in order to reduce the length of the shaft such that the cost of the machine will be reduced. Okay, so in order to reduce the length of the shaft, Okay, we will increase the radius of the rotor. We will increase the radius of the rotor. Okay, basically one thing I'll tell you. Okay, means air around, okay, volume of air around active length will give you normally the power handling capacity of the machine. Okay, of course there is a derivation also, maybe if time permits I will do. Okay, volume of air in the air gap, in the active length will tell you the power handling capacity. For example, just keep it in mind. For example, if I think of this is machine shaft. Okay, so in order to reduce this length, what I do is I will keep like this. So if you think your ceiling fan, just see up and see your ceiling fan. In your ceiling fan diameter will be more and the active length will be less. Okay, have you seen? Okay, now see. So diameter of the motor will be more, means diameter will be more, active length will be less. Okay, active length will be less, diameter will be more. Then what will happen? Means air around it will be same. Okay, otherwise what you are supposed to do, you have to increase the shaft of the length in order to reduce the diameter of the rotor. So of course immediately after this I will show some images also. Okay, so diameter will be increased intentionally in order to reduce shaft length. If you reduce shaft length, cost of the machine will be reduced. That is machine, because huge power handling machine, initial cost of the machine matters. Okay, in machines we do discuss how much will be the cost of the machine and all. Anytime have you ever seen anybody discussing means measuring instrument cost, ammeter cost, voltmeter cost? No, price, what I mean to say is, okay, so price of voltmeter, price of ammeter, it doesn't matter. Price doesn't matter. But what matters in our measuring instrument, you should be able to come to stable conditions soon. Time constant matters. Okay, anyway, in order to reduce cost of the machine, because price of the machine matters, because it will handle huge bulk of power. Now if you think of servos, what we do is length of the shaft will be more and diameter will be less. Okay, so diameter will be reduced, length of the shaft will be increased intentionally. Why? In order to reduce the time constant. Okay, of course some confusions will be there. I will take the responsibility. Okay, so point here is, for example I have one N pole here in the stator. Okay, I have S pole here in the stator. Okay, now I am going to have some conductor from here to here on the rotor, some conductor from here to here in the rotor, some conductor here to here from the rotor. Now if I inject current I, then what will happen? Focus here, please. Now see here, my flux will be, the moment you have current, automatically around that flux will be there. So my flux will be like this. Now what about my N pole flux? N pole flux will be like this, N to S, this pole flux. Okay, so interaction of this blue flux of the conductor and red flux of the pole will be more if you have more active length. In the sense, for example, this is the conductor, blue line, this is the conductor. Okay, in this I am injecting current, around this flux will be there, and here N pole flux is there. Now for example, if this length is less, interaction of this flux, pole flux, and this conductor flux is less, such the torque developed will be less. For example, if this length is more, okay, conductor length if it is more, then what will happen? For a given current, flux will be of more length, then pole flux will be of more length. Interaction of pole flux and this conductor current flux will give the torque developed such that it will be able to rotate faster. Getting my point, right? It will be able to rotate faster. So intentionally active length. Okay, so what is active length? Length of the conductor in the, like where you are going to get the flux interaction of stator and rotor. Okay, of course we will come back to transformer, just stay tuned. Okay, that's why I told you at starting people will be confused. Okay, means this is the way machines has to be dealt, but textbooks they are not dealing that way. Transformer is a transformer, DC is a DC, induction is a induction. That's why we are unable to unify all machines to a single point. Okay, now coming back to the point, see here, if you increase active length, automatically torque developed will be more compared to this length, torque developed, compared to this length, torque developed. Okay, so torque developed will be more, or torque by weight ratio will be less. So torque by weight ratio will be more, such that time constant will be less. Okay, so let me come back again. See here, in machines we are going to reduce the shaft length and we are going to increase the diameter of the rotor, such that shaft length is reduced, and shaft length will decide the cost of the machine, price of the machine can be reduced by reducing length of the shaft. Now, because price of the machine matters, because our machines handle MVA, megawatts of power, MVA of power. Now, if you come back to servo will not handle any power, it will handle only information. Okay, so that information means that information should be transmitted as soon as possible. Means the time constant matter. In order to reduce the time constant, we will increase the length of the shaft. Now people can ask me, sir, here length of the shaft is reduced. Okay, so here length of the shaft is reduced because in order to reduce the cost of the machine, but here length of the shaft is increased. No, so can I say price of the or cost of the servo will be increased? Why? Because mechanical stress will not be there on this particular shaft. Okay, even if our girl's hairpin is sufficient as a shaft here, because means is it transmitting any power? For example, this is the shaft of the servo. Okay, it has to transmit only information. For example, servo shaft is rotating like this. Now who is there to stop the rotor? Load is not there, power is not there, power handling capacity is not there, so there will be nobody to stop the rotor. Okay, if you think of here, means if my motor is trying to rotate in this direction, my load will try to stop the rotor. That's why mechanical stress will be there. That's why cold forging methodology you have to go. That's why price of the machine will be decided by the length of the shaft. But if you think of here, only one side it will rotate. There will be no opposition for the rotation because power handling capacity will not be there. It will just give the information. Okay, so again coming back to here, previously I said one point, that means we do laminate machine to reduce eddy current losses, we do laminate servo to reduce time constant. How we will see in synchronous. Okay, just keep that point in mind. Similarly, in machines, length of the shaft is reduced and diameter of the rotor is increased. Why? To reduce cost of the machine, price of the machine. But if you think of servo, length of the shaft is increased, okay, and diameter of the rotor is reduced. Why? In order to reduce time constant. But increasing length of the shaft will not increase price of the servo, because here mechanical stress will not be there on the shaft. Normally, these two interview questions people will ask. Let us see shaft length. Okay, see here. If you see shaft length here, okay, so this is the active length of the shaft and this is the diameter. Okay, so this is active length of the shaft is less and diameter of the rotor is more because it's a machine. Okay, now next thing is, if I see this moving iron, okay, see here length of the shaft is more. See here, length of the shaft will be more. Or at least if you think of active length from here to here, active length of the shaft is more and diameter should be less. Because it's a measuring instrument. So these are the two important interview questions we have seen. Why do we laminate machine? Why do we laminate servo? At least conclusions we know, feedback of the control system. And second thing is, we know the diameter of the rotor, when it should be big, when it should be small, and the length of the shaft, when it should be big, when it should be less. Of course, we have to add one point here. My machine is so big, my measuring instrument is so small, but in per unit quantities of shaft length, I said, Okay, so in per unit quantities of shaft length, measuring instrument shaft length is more, and this particular machine shaft length is going to be less. And the conclusion from this discussion is, means my machine we are going to analyze the machine by keeping steady state behavior in mind, not transient behavior, because my machine most of the times work with steady state conditions only. So in my machine, steady state behavior only will be analyzed. Of course, few here and there we may have to go with transient also, but main heart of the machine is meant for steady state behavior only. And if you think of feedback path of the control system, they are supposed to be analyzed for transient conditions. Now we will extend to our transformer on load conditions, how we have to analyze, we will see.